Okay, let's go ahead. Number one, what process fuels the sun in its core? Number two, what are the two primary elements found in the sun? And three, list the internal layers of the sun from outside in. You can answer in the chat. Otherwise, my in-person students will answer for us. Number one, Angel, did you want to help us out with that? Exactly. Number one, guys, we got nuclear fusion. Again, vocab due Friday, right? My bad. Vocab due Thursday. No school on Friday, guys. But again, just so you guys know, what keeps the sun lasting for billions of years? It's a process called nuclear fusion where different elements get fused together. And Angel, did you recall what elements did get fused?
Hydrogen.
Perfect, exactly. So think of the sun like a balloon, lots of hydrogen, but also the number one element on the periodic table, which is hydrogen, the most simple element there is. So hydrogen and helium fuse together to create that nuclear fusion. And then lastly, I'll go ahead, or unless Angel, I can answer for you if you want. Perfect, exactly. Remember, there's 6 total layers. We're talking about the 3 internal layers, right? And we had convection zone, radiative zone, and the core. The core always at the middle, right? You can say convection or convective. You can say radiation or radiative. Either one is fine. Just know that they're the same thing. Okay? So again, feel free to have phones for pictures, or you can pause and play it on YouTube when I post it here later today. Questions, comments, or concerns? All right, let's move on to our table of contents. It is the same as yesterday, but update that if you have not already on page 1. Looks like somebody, hope maybe someone in the class gave me a phone call. Let me double check 1 second. Okay, I'll just have to check it later. Oh, no, it was just, it was a note. Just a no call, one of those spam calls, right? Okay, let's go ahead. Let's do our first question of today then. If we look here, give me 1 moment, get the question set up. Hopefully you guys feel pretty solid about it, all about the layers a little bit. Some classes did really well, some classes had difficulty, so I think you guys will be one of those classes that does well, though. Okay, so really quick, only question of the day. This outer sun layer emits a red color and is not visible to the naked eye. So again, humans cannot see it, but we can see it with satellites. It's red, one of the outer layers. Is it A, photosphere, B, corona, C, chromosphere, or D, heliosphere? See what you guys got. Answer in the chat, please. A, B, C, or D. A, B, C, or D. It's red, cannot be seen by the human eye. Yeah. 1 second, Angel. Let me get my phone turned on. Okay. Here we go. All right. Thank you, Angel. I want to give, let's see. Awesome. Thank you, Tatiana, Isaac. Thank you, Irina, Sanaya, Joseph. Thank you. Yorkies, thank you. A, B, C, or D, guys. What's the red layer? Can't be seen by the human eye, only seen by satellites. You got 10 seconds. Irina, thank you. Joseph, thank you. Evelyn, thank you. 4. And participation, guys. 3, 2, 1, 0. I'm going to give shout outs to a lot of us here. We've got Lakia, Evelyn, Joseph, Irina, Yorkies, Joseph, Sanaya, Tatiana, Isaac, and Angel. Fantastic job. The answer is indeed, oh my bad. The answer is going to be actually letter C, guys. Letter C. It is chromosphere. Chromosphere is red. The corona is going to be the outer crown layers that are on the outside. The rays of sun that are white, right? So this is going to be the red layer, chromosphere. Only question of the day. Let's move on to some important questions that could be on that notebook check. We've gone over a lot of the sun. So let's do a full breakdown of the sun with these 3 questions. Again, you need to write these down on page 5. Please write these down on page 5. Number 1, we know the main 2 elements are hydrogen and helium, but I want to know which is there more of and what are the exact percentages. So what percent is going to be hydrogen? What percent of the sun is helium? Okay. Secondly, I want to know if I were to compare the sun to all the planets, how many sets of all of our planets can fit inside the sun? So for example, think of the sun like a candy jar and think of all the planets like M&Ms. Can I fit 50 sets of planets? Can I fit 100, maybe 1,000? What's the exact number that is stated in the video? Okay. By the way, these questions go pretty evenly in the video. I think like in the first minute, number 1, right in the middle, number 2, and near the end, number 3. And then number 3, guys, the sun will end in how many years? How many billion years? And in what way will it end, right? What do we call, Angel, do you recall what we call an explosion when a star explodes? So could it be an explosion? Could it be something else, like it fizzles out or it kind of runs out of energy, right? How is the sun, what's the most accurate estimation as far as how our sun or star will end, right? Something to think about, Okay. And we're going to go ahead and move on because it looks like our in-person students are ready to go, keeping our lesson at a good pace. Give you 5 seconds for a picture if you still need it, guys. 5 seconds for a picture. Okay, so let's check those out. I need the element percentages. I need the sun size comparison with the planets. And then lastly, when the sun will end and what way might it end. Let's check it out. Give me one moment to get this. Again, just a 4-minute video clip, guys. 4-minute video clip here. Three, two, one. 3, 2, 1.
While billions of stars are scattered throughout the universe, the one at the center of our solar system plays a special role for us here on Earth. Our sun formed about 4.5 billion years ago in the Milky Way galaxy's Orion Spur. It was born when a cloud of dust and gas, known as a solar nebula, collapsed. And in the middle of this formation, matter condensed into a burning ball of gas that became our sun. The sun's fiery nature, along with a tremendous gravitational pull and an extensive magnetic field, helped it to become the heart of our solar system. The sun can be divided into 6 layers or regions: the corona, the chromosphere, the photosphere, the convective and radiative zones, and the core. In terms of atom count, the sun is about 91% hydrogen, the sun's fuel, 8.9% helium, and 0.1% heavier elements, such as carbon and nitrogen. Due to the sun's extreme temperatures, these elements stay in a gas-like phase called plasma. In the core, temperatures reaching at least 27 million degrees Fahrenheit, combined with the sun's powerful gravity, fuse together hydrogen molecules to create helium. Called thermonuclear fusion, this releases an enormous amount of energy in the form of radiation, electricity, solar wind, and, as we experience on Earth, life-giving heat and light. Such volatility is contained thanks to the sun's tremendous gravity. It's strong enough to hold the solar system intact and is primarily due to the sun's size and mass. Our sun is the largest and most massive object in the solar system. It's more than 100 Earths wide and could theoretically fit all 8 planets inside nearly 600 times. It also contains approximately 99.8% of all the mass in the solar system. Because of this mass, the sun has a great pull on the fabric of space, creating a gravitational force that causes nearby planetary bodies to be drawn toward it. This gravitational pull allows the sun to hold together a system of 8 planets, potentially dozens of dwarf planets, at least 170 moons, and countless comets and asteroids. Without the sun's gravity, these celestial bodies would drift off into deep space. Another critical property of the sun is its magnetic field, which encapsulates the entire solar system. Called the heliosphere, this force field protects the planets from harmful cosmic radiation. It's caused by the sun's plasma pushing electrically charged particles toward the star's poles. This process turns the sun into a giant magnet. Although the sun's magnetic field is invisible to the naked eye, its effects are noticeable. On the sun's surface are dark areas called sunspots, which mark strong pockets of magnetism. On Earth and on some of the other planets, the sun's magnetic field interacts with their atmospheres, resulting in beautiful auroras. Despite its size and strength, the sun will not last forever. In about 6.5 billion years, it will run out of its hydrogen fuel, expand to envelop Mercury, Venus, and even Earth, and then collapse into a small star known as a white dwarf. In the meantime, the sun will continue to play a critical role in the system that bears its name. The sun's protective magnetic field, tremendous gravitational pull, and ability to create vast amounts of energy will protect, contain, and give life to our solar system.
All right, so a really good summary of everything we've been learning about the past few days. Just like a final breakdown there of that. So number one, what percent is going to be hydrogen versus helium? Yeah, 91% hydrogen, which left us with what percent helium? 8.9, right? So 91.8, or you could say 90. Did they just say 91? There wasn't a 0.8, right? Okay, I'll fix that. So I would say 91% hydrogen, 8.9% helium, right? So again, what's left over of that is basically just some metals, but just focus on those two. Mostly hydrogen. It'll eventually burn out the hydrogen though, and that'll change the sun for sure. We'll explain that in a little bit later. And then how many sets of our planets could fit inside the sun? Yes, 600 times. I think someone in the chat said that as well. Great job, Joseph. Appreciate the participation with that. 600 times the size. So if the sun was like a candy jar and our planets were elements, or I mean, were M&Ms, you could fit like 8 sets of those M&Ms in the sun. And yeah, 100, and you could fit 100 Earths to go around the sun, right? The length, for just the length, of the diameter of it. Yeah, awesome, Joseph. And then number 3, how many years will the sun end? Yep, 6.5 billion years. And did you see what the sun might end up as, most likely? No. Okay, that was a tougher one. I think someone in the chat wants to say it as well. Yes, perfect, Joseph. We have 6.5 billion years. And actually the sun, make sure to write this down, guys. The sun is going to expand first and become a red giant. And what's scary about that is that once it becomes a red giant, it's going to potentially consume Mercury, Venus, and Earth. So although the sun will get a little cooler as it gets larger, it's still going to make our planet a lot hotter because it's getting closer. And then it might eat the Earth. It might consume it and bring it in with its gravity. Now, after that, it's actually going to fizzle out the outer layers, and all that will be left over is the core. And when only the core is left over, we're going to call that the white dwarf. So we're going to get into many types of stars and colors of stars, what colors are hot, what colors are cooler here in the near future. Okay, any questions on that? Okay, that'll be for the notebook check. Let's move on to our last question. This is going to be turned in for points. Again, I'm going to add these for the quarter 4 grade. Again, this is where I use these points to add up to your overall grade. So what I'm going to have you guys do, the students who are online, you can just send this answer to me on Canvas on the Canvas direct message, and I'll count those that are late. I'll be counting those towards your quarter grade. So all I want you guys to do, and let me go ahead and give you the paper slip here, Angel. Write your name kind of small on one side. That's right. What you guys are going to do is we're going to answer this question. Okay, and again, you guys are going to send this to me. It's the last thing we're doing today. You guys are going to send this to me as a message on Canvas for the points. Okay, so for example, when a lot of you guys say an overall grade, you had like an 86, but you have great participation and you got points from the quizzes or these tickets that I do in the middle of classes. I use these to bring your 86 to a 90, right, at the end of the quarter. So again, don't answer in the chat. That's a good answer though, Joseph, but don't answer yet because we're gonna watch a video that answers it for us. There are 3 big problems that arise from this. So why can't we just launch? Our sun would disintegrate our trash, no problem. The sun would eliminate and get rid of it, no issues, no problems about it. But there's some logistical and some process issues in regards to getting it to the sun and things like that. So I want to know specifically, why doesn't NASA, why can't we just launch all our trash into the sun? Why can't we do that? Let's go ahead and find out. Last activity of the day, guys, last activity of the day. I do need to explain the article assignment with you as well. Let's do next week after this real quick. And again, Angel, before I can answer, and guys, just so you guys know, I won't be answering the answers for this because I want to make sure you earn the 10 points. So, and then Angel, I'll let you know once I end the class after you turn in your paper slip. Let's check it out, guys. 3 big problems. Again, why can't we launch trash into the sun?
Welcome to your new landfill. A giant ball of burning gas that we call the sun. With surface temperatures of 5,500 degrees, it could obliterate any type of trash we throw at it. From pesky plastics to nuclear waste. And with everything we're launching into space these days, surely it wouldn't be too hard to send a little trash to the sun. But how much would it cost? What dangers would be involved? And why would it be easier to send a rocket right out of our solar system than it would be to get anything to the sun? This is What If, and here's what would happen if we sent our trash into the sun. Our planet is filling up with garbage. Yeah, at the rate we're going, by 2050, we'll be dealing with 12 billion tons of plastic sitting in landfills. That's 35,000 times the weight of the Empire State Building. Sure, it'd be nice to put it all in some giant rockets and blast it off, but there would be some serious risks involved. Like, what would happen if there was an accident while a rocket was in the Earth's atmosphere and all our trash and nuclear waste came raining back down on us? The sun is about 150 million kilometers away from Earth, so getting any trash there would be extremely expensive. To put it in perspective, the Ariane 5, a modern European rocket, has a payload capacity of 7,000 kilograms and costs approximately $200 million to launch into orbit. So to get all the planet's garbage headed off towards the sun would take 168 million of these rockets just to remove our trash for 1 year. The price tag would be $33 trillion. And that's just the cost of getting the rockets into orbit around the Earth. If we wanted to get them from the Earth's orbit to the sun, it would require 10 times more fuel. Okay, we get it. It would cost a lot of money, but that's just the beginning of our problems. You see, Earth moves around the sun at 30 kilometers per second in a direction that's basically always sideways relative to the sun. If you were to launch a rocket from Earth straight towards the sun, it wouldn't lose that sideways speed, and so it would miss its target. The only way we'd be able to get that rocket right into the sun would be if we could cancel out all that sideways motion by slowing down the rocket by 30 kilometers per second. How tricky would that be? Well, put it this way, if we could speed up the rocket by 12 kilometers a second, it would have enough momentum to get out of the solar system. So let's simplify that a bit. To crash into the sun, lose 30 kilometers per second. To get out of our solar system, gain 12 kilometers a second. Getting to the sun takes 3 times the effort. For the sake of efficiency and fuel costs, it's better to go to the outer solar system, where the rocket's speed would be lower, then use a little booster juice to fire the engines enough that the rocket and its load of waste would fall into the sun. Even if we were able to figure all this out and successfully deliver our garbage rocket directly to the sun, it probably wouldn't be worth all the risks involved. What risks, you ask? Well, for starters, Let's say we've got our first rocket all loaded up with a bunch of nuclear waste, and just as it's about to take off, it explodes on the launch pad. Now we've got some fun nuclear fallout to deal with. But maybe we're a little luckier and the rocket launch itself is successful, but it explodes once it's in orbit. The best case scenario here is that we add a ton of debris to the already growing problem of space junk circling the Earth. The worst case scenario is that our exploding rocket, packed with thousands of tons of household trash and spent nuclear fuel, comes crashing back down on us. Either way, it's not good, and this whole operation really doesn't seem worth it. Maybe instead of looking for these outlandish solutions, we should just, stop producing so much waste. Or we could just say, who cares, and see what happens if we start dumping it in volcanoes. But that's a topic for another What If.
Okay, so interesting ideas. We could watch the volcano one another day, but again, I can't necessarily go over with you all those because I want to make sure you get the points for them when you send me the messages on Canvas. So go ahead again, send me the 3 big problems that are the reason why we can't send our trash to the sun. The 3 big problems. Just list them out, 1, 2, 3, and I'll give you those full 10 points, and those will be added at the end of the quarter. Those are part of our participation, and they add up. Trust me, you'll see your grade jump up a bit with each of those as we go. Let me go ahead and explain one more thing, and Angel, turn that in whenever you're done with it. I got one more thing to explain, guys, before you guys head out. We already know the vocab, right? That's due on Thursday. This right here. Okay, a lot of these are already in our notes, so hope you get those from the notes, 1 through 8. Again, if you want the full credit, we're starting the quarter off strong. We're going to be on a positive note. I don't want people turning this in in May and stuff, and I have to give them barely, 30% credit or half credit, right? So turn this in right away. I mean, if maybe I may not even give any credit, right? So make sure you turn that in during the due date. If you want the full credit, make sure you have the sentences with it and the illustrations. That's due in 2 days. Okay, but let's look at the newest assignment. We have 5 article questions, and you got to read 3 short articles. You can send these in typed through the submit. You can type these out and send these in. Just put the numbers in your answers. They're all about things we've been learning about. So article number 1 is going to get into satellites and humans interacting with these solar satellites and solar satellites in general. And that's 2 questions. Article number 2 explains solar wind and auroras. Okay, and article number 3 is going to go over solar storms and Earth's weather. So read those. They're quick. They're easy, quick things to read and answer the questions. I'm looking for short paragraph answers, 2 to 3 sentences maximum, right? 2 to 3 sentences. Okay. And again, if you go to Canvas, go ahead and pull up my Canvas 1 second, guys. One moment, just going over to our class now. Be done in a minute, guys, done in a minute. All right, so if you, again, go to Canvas, and you should see solar article assignment posted. All right, so you can either go down here. Here's where the video lessons are at. So you can either scroll down the home page and click right here where it says solar impact articles, or go to where it says assignments up here. Someone's already got their vocab done. That's awesome. Assignments, I go to solar impact articles. All right, and I've got the 5 questions there again. And I've got the articles that I need to read as I scroll down. Okay, 3 is really short, 2 and 1 are kind of medium, right? They're bolded and numbered. All right, so go ahead and take attendance and we'll call it a day.